Hi, it's Kate, and this is the third video for week/fortnight 7 of Math 23B. The final thing we're going to do in Tuesday's lecture, depending on if we have time, hopefully we will, but at least when we come back from break, is that we are going to prove the Ascoli-Arzela Theorem. Sometimes this is called the Ascoli Theorem. You'll see the names reversed sometimes in the literature. But what's really cool about it is that it's an extremely elegant, beautiful proof that draws all of your analysis skills together with this new understanding of sequences of functions. So let's take a look at the statement of the theorem first. We're going to have a sequence of functions. We label them f sub k of x. They're defined on the interval from 0 to 1 inclusive, and they map to the real numbers, each of which is even better behaved than what we require for Riemann integrability. Note that each of these functions in the sequence is bounded, and it is uniformly bounded. So that means that there is some constant r that's greater than 0 such that the function values, the magnitude of the function values for every single function in the sequence is less than r for all the functions and across the entire interval from 0 to 1. Note that each of the functions is continuous. Furthermore, the entire sequence itself is equicontinuous for each value of x. So that means, note that that's not uniformly equicontinuous though. That means for any epsilon greater than 0, there exists a delta greater than 0 such that that epsilon delta partnership that's created for some custom x will ensure an output, the function values are within epsilon of each other at that particular x, and that works for all of the functions in the sequence of functions. And our conclusion, given this fact that we have a sequence of functions that's uniformly bounded and equicontinuous, that there's a subsequence of these functions that converges uniformly to a continuous function in its limit. Now, this is pretty tricky. The proof strategy can be overwhelming if you don't break it down into distinct parts. Now, we're looking at the conclusion line here, right there, and I'd like to point to 3 specific moments that each part of the proof is going to get at. So the first thing is there is a subsequence that converges uniformly. All right? Our first part is going to find that convergent subsequence. That is part 1. We show that we can extract this convergent subsequence. We're going to show that it converges for rational x. Then we're going to show that it converges for irrational x. So we've basically shown that it converges over the entire interval from 0 to 1. It converges for every real value for x in there. Then we're going to show that it converges to a continuous function. That'll be our second part. And then the last part is going to be that that convergence is uniform. That's going to be the third part. This is your proof, 20.1, but take a look at the front of your notes packet. The convergence to the limit function is uniform, is not part of that, so the only things that you need to prove are what I've underlined in red and what I've underlined in blue. You do not need to prove that last chunk that the convergence is uniform for 20.1. But the red part and the blue part of the theorem, that is what we're going to prove for 20.1. We'll show the entire thing in this general proof strategy outline here. So let's take a look. I'm going to talk through the proof structure now that you understand the 3 parts that are at work, and then we're going to go through it in great detail in class. This proof is so cool because it relies on so many things that we've done this year. Let's start at the beginning. The first thing we're going to do is we're going to look at that closed interval from 0 to 1, and we're going to enumerate the rational numbers, which we know we can do from that previous proof that we did in the fall semester, that the rationals are countably infinite, and so we can enumerate them. We can construct this sequence of rational numbers where we apply a serial number to every single rational in this particular interval. All right, let's take a look at our next step. What we're going to do is we're going to take the very first rational number and we're going to plug it into our sequence. Now all of a sudden our sequence of functions turns into just a sequence of function values. And note that this is a sequence that is bounded because up above we knew that all of the sequences f sub k of x that sequence was uniformly bounded. So by taking our first rational number, x sub 1, and plugging it into our sequence of functions, We have a sequence on a bounded compact set, and from that we can use bolzano-weierstrass to extract a subsequence. Now that means that only some of the functions will offer up function values for this first rational number that are going to be used in the subsequence. Now, if we looked at just those functions that are used in our convergent subsequence for the first rational number, and we plugged in the second rational number into just those functions that are used in the subsequence, we now have another subsequence that's on a compact set, and so we can extract another subsequence that is convergent when evaluated at the second rational x sub 2. And from that, we can extract another subsequence that's convergent for x sub 3. Then plugging in x sub 4, we can extract another subsequence that's convergent for x sub 4. And this is how we are going to construct our particular convergent sequence of functions. We're going to use the first element from that first subsequence, the second element from the second subsequence, the third element from the third subsequence, and so on and so forth. This will be more clearly done out using diagonal construction and really showing you graphically what's going on. And what's interesting here is that note that since each subsequent subsequence comes from the subsequence before it, right? Eventually, for every single rational x, this will be a convergent sequence. This diagonal construction guarantees eventual convergence for all rational x because that's how we constructed it to behave. So that is part of what we underlined in, I believe, red up top, that we have a subsequence that converges. Now the question is, great, it works for rational x, but does it work for irrational x? That is going to be the second part here. We're going to exploit equit continuity to show that this converging sequence of functions will converge not just for rational x, but also for irrational values of x. And we're going to exploit equit continuity and use that epsilon over 3 trick there. So this part, right up here, constructs a convergent sequence of functions for rational x. This section right here, exploiting equit continuity and using the epsilon over 3 trick, will allow us to show that this convergent sequence that works for rational x also works for irrational x. And then now that we've shown that, great, we have proven the red part that we underline up top in 2 steps. First, by its construction that works for rational x, and second, that it does also work for irrational x, which means that it will work across the entire interval from 0 to 1. We're then going to move on to part 3, which is the blue part, that it is a continuous function. So we're going to exploit equit continuity again and use a little bit of the triangle inequality as well to show that, yes, we can demonstrate that it is going to be continuous. Finally, we can layer on top the green part that it is uniform convergence. This is not a necessary part of the piece of the proof statement we give you for proof 20.1, but the complete statement of the Ascoli-Arzela Theorem does require to show a proof of uniform convergence. The only reason I'm not going into great detail about this is because this is exactly what you'll be doing in lecture. But I think the important part to note is that in order to prove this statement, that there's a subsequence of the sequence f sub k that converges uniformly to a continuous function, the key that you need to know to go into Tuesday's lecture is what we're going to do first is to create that convergent subsequence. We're going to create it based on its behavior with the rationals. So just by construction, it already converges for the rationals. We're then going to stop and show that that same subsequence that we just constructed works for irrational x. And then we're going to show that that subsequence converges to a limit function that is continuous. And those are the 3 parts necessary for proof 20.1. And then at the very end, we're going to layer on top that the convergence to this limit function is uniform. So those are the pieces of Ascoli-Arzela. And in order for you to sort of get the most out of Tuesday's lecture, you understand the pieces and how they satisfactorily prove this conclusion, even if you're not sure of all the details. You just want to understand the big parts of this argument. If you have any questions at all, please don't hesitate to ask. But of course, this lecture preview video is nothing without the lecture that comes after it. So come back to this video, rewatch it, understand the major parts of the proof, how they work together, and inside the proof, and that'll give you a great sort of working knowledge of how to tackle this proof to avoid memorization, which is certainly no help with a proof this long. And this is the longest, I would say, most challenging proof for a lot of students, but as long as you have these 3 parts clear in your mind for 20.1, that we're going to create a convergent subsequence for the rationals, we're going to show that it works for the irrationals, and then we're going to show that that limit function is continuous. It's going to really help organize your thoughts in the long run. Thanks for listening, guys.